it's going to start switching on soon to record. Yep, there it goes. Okay, right. So welcome. We're going to be doing something very similar to what we did for the mechanics, if you were in that session. I'll be going through a 2017 paper, and as we go through it, I'll be hopefully giving you some tips and tricks on how to approach these sort of questions. So I hope you can all see my shared screen where you've got, I'm just making it bigger, where we're going to look at the acids and bases paper. Now, this is a science standard. So if you're doing this in the chemistry course, make sure that you don't sit this exam with your any other chemistry exam. The chemistry standards are set on a different day to the science standards. So this will be, for the person with the camera on, I am recording. So if you want to switch your camera and mic off, unless you want to be recorded, thanks. So the mechanics, the genetics, and the acids and bases are set on one day, which is a science day. The chemistry standards are separate on a chemistry day, and the physics standards of the electricity, heat, and what's the other one, waves, is on a separate day as well for physics. Okay, let's get going for this. You'll notice, again, like what we did last time, you can get all the past papers and the assessment schedules and so on if you just Google 90944 and NZQAs. So to show you what I've got here, whoops. So this is where I've Googled it. It's obviously a little bit too small for you to see at the moment. I'll make it a little bit bigger. But you can see if I have this, I've got all the achievement standards. So it's had quite a few variations. That's the latest one. And this is where you get the past exam papers. So you can get them in English and Te Reo Māori. And then, of course, you have got a resource booklet as well. So make sure in the exams, whether it's the derived grade or the final, you should be using this resource booklet. So here's a 2021, the 2019 paper, and it goes all the way through to 2011. Sometimes they give you real live examples of student work. So students that had sat, say, the 2016 exam, and this one got excellence, this one got merit, this one got achievement, if you sort of want to see how the marking works. But as I said, it goes all the way to 2011. And if you scroll down further, then you get the assessment schedules. So for example, I've got here, oh, sorry, that's the Te Reo Māori one. This is the assessment schedule. So you can, if you're practicing, you can check to see what's an achievement, what's with merit, what's with excellence. I tell my students they're welcome to work through a past paper and upload to the SEO 1054A Dropbox if they want me to have a look at it. So you can ask your teachers. If I'm not your teacher, you've got somebody else, you can ask them as well. Okay, so any questions about where to find that information, the past papers, the assessment schedules, and the resource booklet? You're all pretty clear? You can put into the chat, that should be at the top. It's got people chat. Okay, right. So because practicing goes, you know, it is very useful. In fact, I remember an examiner telling me if somebody has worked through 10 past papers, then they deserve to get excellence. Because I was saying, oh, you know, it's the same sort of questions coming up. But, you know, you should really know your work if you've gone through 10 past papers. Okay, so what do you need to know? You need to know the atomic structure and up to the first 20 elements for the electrons and and ions. You will need to know some other elements as well, but only for the electron arrangements will only be limited to the first 20 elements. And you need to be able to write the name and give the formulae, but it'll only be limited to what is given in the resource booklet. You need to be able to explain. So explaining always is like excellence level things. So that also includes the rates of reactions. And then, so it's everything around about acids, pH, salts, and so on. And then you need to be able to describe some uses as well. I hope I got that person in. I'm not sure if I managed to click on time. Right. Okay. Please make sure that you learn these formulae as well, so you recognize them. They should, in the exam, tell you what it is. They might say, for instance, calcium carbonate is reacted with hydrochloric acid, and then they normally have in brackets or in commas after that, they give the formula. So you should have those there in the questions. Oh, great, Kenzie, that you admitting everybody. That's fantastic. I didn't realize that you could do that. So keep on admitting them. Right. So you've got usually the name given and the formula, but just to make absolutely sure, learn these off by heart. So if I say sulfuric acid, you go H2SO4. If I say nitric acid, you go HNO3, because you will be asked at least 2 of these in the exam, guaranteed. Okay. You'll also be asked their reactions of any of those 3 acids with a metal oxide. So it could be, for instance, like silver oxide or calcium oxide or something like that. A hydroxide, so like calcium hydroxide. I'm just abbreviating to formulae because it's shorter to write. And then also carbonates and hydrogen carbonates. You may be given other acids, but they will tell you what those acids are with their formulae if needed. Okay, you'll always recognize an acid because an acid needs to have a hydrogen in it somewhere. Okay, if it doesn't have a hydrogen in it, it's not going to be an acid. So for example, NaCl cannot be an acid, or CaCO3 cannot be an acid because there's no hydrogens on there. There are some exceptions, like if you had ammonium nitrate, that's got some hydrogens in, but it's not a, yeah. There should be an H in the front for it to be. Now you are given a table of ions, so please make sure you use it so that you may think you know sulfate is SO4 2-, but just to be double check it, unless you're absolutely sure, I would make sure that the resource booklet is open next to me while I'm answering the questions, and I double check. Now, a way to remember, because sometimes students get confused, they go, oh, what is this thing, and so on. If something has, let me do D. If you've got what we call a polyatomic ion, so you've got 2 elements in here. You can see I've got a C and an O, so they're both capital letters, so it's 2 elements. Here I've got an N and an O, they're both capital letters, so you know that's 2 different elements. Compare that with a C and a U, but that's a small u. So you know that this is 1 element because an element symbol, if the second one is a lowercase, it belongs with the C. Okay, so that CU is different to that C over there. And that's why, if you're wondering why your teachers are getting a bit anal about if you write, for example, CO3, we sort of start jumping up and down, because CO3 like that is not carbonate. you're actually talking about cobalt, because you made the O, instead of a big uppercase or capital letter O for oxygen, you've made it a small letter O, so you're talking about cobalt. So be very particular that you follow the chemistry conventions, because there's a big difference between carbonate and cobalt, I can tell you that. Okay, so going back to, if it's got an O in it, then you know that these names will end in 8. Okay, they end in 8, and I always say, think of 8 a donut, because a donut is a nice big O. So if you've got an O in it, they end in 8. So this will be oxide, but this will be carbon 8, because of that O in there ends in 8, and the first part, whatever that element is in the beginning. Now, sometimes we do abbreviate it. So here we say carbonate, but here we don't say sulfurate. We simply say sulfate. Okay, yeah. Here, again, we don't say nitrogenate. We just simply say nitrate. So nitrogen, we now just say nitrate. So that's just helpful if you're trying to remember what these are and you're trying to work out, do I choose this one because I've got sulfur there, or do I choose that one? So if you know there's oxygen present, or if it talks about sulfate, you know you've got to choose this one because of the 8, whereas this would be sulfide. Okay. Any questions about this? So recognizing what these ions are. Yep. Okay. And then, as I say, you are given these other ones, and you are expected to recognize them, that this is silver, this is lead, and this is iron, and that's iron as well, but it's iron 3, and that's iron 2. We use Roman numerals for iron, because don't just say iron, because I wouldn't know if it is the Fe3 plus iron or the Fe2 plus iron. So always use those Roman numerals. So this would be iron 3. Okay, so that's the first thing you are given, the table of ions, and being able to write formulae correctly is needed for merit level. To be able to write balanced symbol equations is needed for excellence level. So you need to be able to write formulae correctly. You are also given a periodic table. So hopefully you know round about there is a sort of a cutoff line, more or less. All of these are non-metals, and all of these on this side are metals. And this standard revolves around ions. So you get ions when a metal atom combines with a non-metal atom or atoms, okay, you will get ionic bonding. So you'll have ions being formed. So cation, the metal forms the cation, the positive charge, and the non-metal forms the anion, which is the negatively charged. So your sulfide, your oxide, your chloride, your fluoride, your bromide, your iodide, etc. Those are the ones you use, or the ones common over here. You would have those over there that you need, these over here that you need, plus a few over here. You've got your lead over there and your silver and your iron. That can go both ways. So not too many extra. Oh no, cations are positive and anions are negative. I know there's in the module a picture of like a cat, and it's sort of showing the nose as being a cross. I don't know if that's a good representation, But if you can think of a good mnemonic that cations are positive and anions are negative, please try and remember it that way. And again, if you've got the periodic table, then what's useful is anything in group 1, if it becomes a cation, it's because it's got one valence electron, so only one electron in its outermost shell, it's going to lose that one valence electron to form a +1 charge. Anything in group 2 is going to have 2 electrons in its outermost shell, so it's going to lose both of those, so it'll form a +2 charge. That's why we have magnesium 2+ and calcium 2+ and so on. Skip all those for now, and then we'll go to group 13. The only one you need is this one over here. Don't worry about the rest. And think of it as having 3 electrons in its outermost shell, so it'll lose 3. So aluminium still, it's on the border between a metal and a non-metal. It's sort of a metalloid, but it's got more metal-like properties, so we still put it with the metals, and that'll form a 3+. And then all of the ones in group 16, they have got 6 valence electrons, so it's much harder to lose all 6 electrons, because if you think about it, if oxygen loses 1 electron, it's now got a positive charge. Now I've got to take a negative electron away from something positive, which it's being attracted to, so it's going to be harder. And if I've managed to remove 2 electrons from it, now it's doubly positive charge, and I'm trying to get another one off. So it's much easier to actually gain electrons. So these over here in group 16 will gain 2 electrons. Okay, I put a plus for gaining, but it's going to have a -2 charge to get a full energy level. And anything in group 17 is going to gain 1 electron. Yep. And yep, so that's Quinn, that's the way you would go. So if you round up when you're on this side, and you round down on that side. So if you've got an electron configuration of, say, 2, 1, it's going to lose that 1, it's going to round down. But if you've got it of 2, 7, then this one will get rounded up and it'll become 2, 8 to get that extra electron. So I hope that sort of answers things. Okay, another one to just remember, these are given in the table of ions. If you wanted like a shorthand method though, if I just change a color to something different, you can remember these fairly easily if you've got the periodic table, and that you can go, this one's 1, that one's 2, and that one is 3. And you know it's 3 because of that. So it's sort of like a diagonal. So zinc, yeah, it actually has got lots of electrons in its outermost shell, but it actually only has got 2 in the 4th energy level. It's actually similar to calcium that way. So zinc and calcium in your body can replace each other quite readily. So that's zinc. And then silver, although it's mucky, it's got lots of electrons, but it'll only lose ever 1 electron from its outermost shell. So it'll only lose 1 electron to form an Ag+ charge. Okay, right, so use a periodic table, because it really helps to work out, is it a metal, is it a non-metal? So which 2 things are going to react together to form my bond? So I'm not going to get chlorine reacting with sulfur to form 2 anions, okay? Because these are going to be the anions, and anions are going to repel each other. So that's not going to work. Okay, let's get going, because we've spent now a lot of time and we haven't even started the paper. Now, pretty much the way the paper works is you're going to get one question all about atoms and ions and electron configurations and things surrounding that. you're going to get one question on rates of reactions. They'll bring in other bits as well, but it's really all on rates. So how does temperature affect the rate of reaction? How does surface area affect the rate of reaction? There'll always be a question like of that. And then there'll always be a question that's on acids and bases and pH and color changes and salt formation and that sort of thing. So, and they can come in any order. So you can have in some past papers, rates of reactions come first, like over here. In other exam papers, or the one you're going to get, the rates of reaction paper may come last. So expect it to come in any order. So here we've got, and notice, for instance, we've got our sodium hydrogen carbonate, and they give you the formula in this case. And can you see there's sulfuric acid, and they give you the formula. So make sure when you're writing the word equation, you use the words, and if you're writing the symbol equation, you use the symbols. And they say, right, we've got at different temperatures. So immediately in your head, you need to think of how does temperature affect a reaction rate? And remember, temperature is the only one that affects it in two ways. So this would probably be an excellence level question because you've got to discuss both of those ways. Surface area, concentration, and catalyst only affect them in one particular way. So first of all, you've got to say what causes the fizzing. So although this is a rates of reaction question, they are bringing in some acids and bases. So hopefully you saw the word carbonate, and the general equation is acid plus carbonate gives salt plus water. Sorry, I'm just, you would write this out. Kenzie, did you want to say something?
Yes.
Uh-huh.
And carbon dioxide, because there's a carbon and oxygen.
Correct. Correct. Yep. So if you were giving a word equation, you would write the name of the acid, the name of the carbonate, the name of the salt, and you'd write water and carbon dioxide in words. I'm sort of doing it semi just to try and fit it in here. So that's the one general equation. If you had the other one, which is just acid plus base, then you're just going to get salt plus water. By base, I mean an oxide or a hydroxide. So in this case, what causes the fizzing? You would say a carbonate reacts with acid to give off CO2 gas. And my writing is terrible, but hopefully you can understand it because I'm speaking at the same time. So that would be a straightforward achieve level question. Okay, just to make it get started, that hopefully you know that. Now, this is where the rates comes in. When you see words like fastest and particle collisions, you know this is a rate question. So when you think of rate, in your mind, you need to think of key words like frequency of collision. Don't just say more collisions, because I always say, if I say in the road next to me on my right, there are 2 collisions, and if on my left the road has 10 collisions, which one is the more dangerous road? You would probably think the one on my left because it had 10 collisions. But if I then said, oh, but I meant the one on my left had 10 collisions in a year, whereas the one on my right had 2 collisions a week, which one would you now say is the most dangerous? So that per second or per time period is really important when you're talking about rates. Don't just say more collisions, because that's too vague. Okay, so why would it be fastest? So remember, you're adding a solution over here. Whoops. So this is a solution, and this is a solid because you're told it's a powdered thing. So you're adding a solution to it. Why do you think there would be, at the beginning, as the reaction first starts, why would it be really fizzing a lot and then the fizzing sort of slows down?
Because you run out of chemicals to react with each other.
Yep. So that's correct. And I'm glad you answered like that, because you know, you've got that picture in your mind and it is correct. But in order to do well, I always say explain, and the people that came to mechanics, you know, think about it as though you're explaining to a 10-year-old. Think of all the obvious things you need to say so that the examiner can be clearly see that you've understood it. So it is about the number of particles, but you've got to think of, in the beginning, it helps to sort of picture it. You don't have to draw the pictures, but in your mind, in the beginning, there are lots of particles, but in the end, all that acid has sort of been used up, or there's very little left. So what I've got here is lots of particles in a unit area or volume, and here I've got few particles. So this is in the beginning. I have a high concentration of acid particles, or H2SO4. So there is a greater frequency of collisions. So the reaction rate is fast. Try and always picture what is happening, what's happening to the particles. If you can picture that and then try and describe that. Oh, okay, Kenzie, sorry. Okay, fine. Kenzie, describe it to a 2-year-old, okay? No, that's fine. I just find that hilarious, actually, you having to explain it to somebody who's older than you. So that the reaction rate is high, or it's a high or fast or something along those lines. Okay, so notice I've got a high concentration. Now for excellence, as I said, do the obvious. What does it mean by high concentration? So whenever you made a statement, go back, look at it and go, why, how? How can I add more extra detail? So in the beginning, there's a high concentration. What do I mean by that? So high concentration means there are lots of particles, or H2SO4 acid particles, per unit volume. So whenever you explaining a rates, always give the definition of what you're talking about. So in this case, because it's about concentration, we've got the high concentration in the beginning. You should always define what you mean by concentration, the number of particles per unit area, and then explain what it's about. So because I've got a high concentration, I've got a greater frequency of collisions. So if you now look at the assessment schedule, now this is a bit small. I'll try and make it bigger. Okay, so can you see you've got in the beginning that you've got a high concentration, and can you see they've explained the concentration, what it is? The greatest number of reactant particles per unit volume. So they've explained that. Okay, and therefore, can you see those keywords, frequency, and actually what they also like is something like effective or successful collisions. So learn those key words and use them in your explanation, because it really just takes a bit of practice and you can get excellence with these. Right, let's carry on. Okay, I haven't answered absolutely everything, but I've done most of it. Now you will always, well, nearly always be given a graph of some sort. You might need to draw on the graph, or you might need to just simply interpret. So here they've looked at the amount of gas that's been produced. And what you can see straight away from this one is there was lots being produced at 55 degrees and not much or not as much at 30 degrees. So it also says refer to the graph. Now, please, when it says things like that, it says on the previous page simply because I've moved this one down so it's on the same page. Refer to the graph. So make sure you refer to the graph. So say the one at 55 degrees has a steep start to the graph compared to the one at 30 degrees where the slope is not as steep. Do you see what I mean by referring to the graph? Don't just say at 55 degrees, it's a faster rate of reaction because I have not related it to the graph at all. So make sure you're saying it starts, the slope is steep and then becomes less steep until it's horizontal. And when it's horizontal, that means the reaction is finished or complete or something like that. Now, so that's the first point. Make sure you refer to the graph. The second one is when you've got temperature, you must talk about the 2 points. And with temperature, the key word here is kinetic energy. I know I always leave sort of jokes whenever I give feedback, and I've got always a little picture that I use of the thermometer is the speedometer of atoms. And if you think about it, what does a thermometer do? It measures temperature. So as the temperature goes up, and if you think of temperature then being the speedometer of atoms, are the atoms moving faster or slower? What do you think? Okay, so as they go, as the
Faster.
faster. Yep. So and if they're moving faster, kinetic energy is the name of the energy we use for something that is moving, something that's moving. Okay, so if you are increasing the temperature, you're increasing the speed of the particles, and therefore they have a greater kinetic energy. So make sure you put that, link that together. The next,
which also means that they have a higher, which also means that they have a higher probability of having a successful collision because they're moving around faster.
Yeah, and we're going to break that into 2 bits. So if they're moving around faster, they will collide more often per unit time. So there is a greater frequency of collision. And simply because if you think about it, if you're walking around a room compared to if you're all running around a room, you're much more likely to collide when you're all running around the room than if you're walking around the room. So you're moving faster, you're going to meet up more often. So that's the first thing. So you would be talking about that, a greater frequency of collision. Then the third point you need to raise, because remember I said there were 2 parts to the temperature effect. The first one is moving faster, greater frequency of collisions. And then this one is a really important one, is that a greater proportion of collisions exceed or is bigger or something like that than the activation energy. So in other words, when they meet, in order to actually change from the reactant particles to a product, they need to slam together hard enough to be able to do that. If they don't slam together hard enough, they're not going to change. So I always say, as an example, if I've got, for instance, at 30 degrees, I have, say, 2 collisions per second. And at 55 degrees, I have, because I've got a now greater frequency of collisions, I've now got, let's make this easy numbers, 10%, 10, okay, 10 collisions per second. And at 55 degrees, I have, let's say, make it 20, just to keep the thing simple. I've doubled my number of collisions, okay? Now, the second part is the greater proportion. At 30 degrees, only about 10% of those, I'm just taking figures out of the air, but because they're moving more slowly, they're not slamming together very hard. So only 10% of those collisions are actually going to be successful. So what I'm going to be having here, 10% of 10 is really just 1 collision per second is actually going to result in a change. Okay, compared to, say, at 55, they're going a much, much, much harder. So we're going to be saying 50%, half of them will now, when they collide, will now have a useful, or they'll have a change. So half of 20 is 10. So instead of 1 collision per second, I'm now going to have 10 collisions per second. Can you see the effect the second one does by a greater proportion? So you must mention both of these. Any questions on that? Is that clear? Have I made that sort of stick in your mind to put both of those in there? Okay, right. Now, very quickly, because time is going, so what we're going to be doing here is the word equation. So you are given the starting point. So please, please, please start by writing what is given. Okay, no excuses for not being able to write this. Goes to, okay, and I'm going to write it here, NaHCO3, because I'm just simply copying from the given things. Okay, now you've got to go, okay, what are my products? Well, with an acid and base, you're always going to have water. So put that in straight away. And you're always going to have a salt. Now, for a salt, it's going to be the cation of the base and the anion of the acid. So it's not very easy to see over here. So I'm going to say cation of the base and the anion of the acid. So if I wrote it in here now, I've got NaSO4. Yep, so it is going. Now, go to the table of ions to go Na plus and SO4 2 minus. So how many sodium ions do I need to balance that 1 positive charge to balance the 2 negatives? I need 2. And the way you do that is the bottom right corner has been reserved for giving the ratio. So in other words, in this unit, I've got 2 sodiums with 1 sulfur. Chemists are lazy, so if there's no number there, then we always assume it's a 1 and 4 oxygens. Yep, so 2 sodiums to 1 sulfate. Let me just remove that 1 because it's... And now the final thing is, if you have a look, I've used up the sulfate, I've used up some hydrogens, I've used up that, but I've still got this left. So if you didn't know before, go back to that first question, what was being released, and hopefully, even if you didn't know there, you'll know now it has to be carbon dioxide. So this will be sodium sulfate plus carbon. They don't actually, if you wrote just this one down and you got it all correct beautifully, they're not too fussed about this. This is just simply an achieve level question for those that don't know their formula or can't write balanced equations. So now we've got to balance it. So we go, okay, I've got Na, H, C, and O. Okay, didn't quite fit it in. Always start with the simple ones. Na is 1. There I've got 2 on the other side. So that's not balanced. The only way you can balance is put a 2 in front. You can't change the ratio once it's been fixed. Yep, Quinn, I know you are onto it. So that now changes it to 2. And for sulfates, I always do hydrogens and oxygens last. For sulfates, I've got 1 sulfate here. I should have put sulfate. So 1 sulfate here and the other one there. So I'm keeping sulfates separate to the oxygens. So they're 1 on 1. Then now I've got here 2 carbons. So I've got 2 carbons and I've only got 1 carbon there. So I need to put a 2 in front. So I have 2 in both. And now we have oxygens. So I've got 2 times 3 oxygens on this side. I've already counted for sulfates, so I'm ignoring that. So I've got 6 oxygens, and here I've got 2 times 2 is 4 carbon dioxide, so I need a 2 in front of there. So 2 times 1 is 2, so 2 plus 4 is 6, and then my hydrogens should work out. So 2 hydrogens here plus 2 hydrogens there is 4, and 2 times 2 is 4. If anybody is not sure what I've done there and you're going, then organize a online lesson with your teacher so that that can be sorted, because balancing is required for excellence. Okay. So that is that, and you will be normally given like 2 equations to balance in an exam paper. Now, let's have a quick look at this one. So we've got sodium and potassium, but notice in this case, they have not given you the symbols. So they want you to recognize where sodium and potassium are. So you look over here, and hopefully you can recognize that that is sodium and that is potassium. Okay, I always think of, because there's an H up top on the top of group 1. So I say, hi Lionel, naughty kitten, to help remember the N and the K, or you could say, hi Lionel, sweet, the S for sodium, puss, potassium. So you could think of it like that. Just to try and remember that sodium is Na and potassium is K. Right. Going back, oops, over here. And the other thing you need to know is oxygen gas, it is a non-metal, so we're not going to get any element by itself like that. Oxygen is just way too reactive to sit there with only 6 valence electrons and not do anything. So oxygen gas is always O2, just in case you were asked for a question. Because sometimes when you read through it, you try and think of what is happening. So they say these react with oxygen, but sodium and potassium don't react with each other. So hopefully you know sodium and potassium, they are metals, and oxygen gas is a non-metal. And remember what I said, when left reacts with right, you get that ionic equation, or it forms ions. So pretty much, why do sodium and potassium react with oxygen but not with each other? Because sodium and potassium are metals, oxygens are non-metal. That'll get you started, but you must now refer to electron arrangements of the atoms and the ions. So highlight to make sure you answer every part of the question, because you can get achieved easily, but you won't necessarily get excellence if you don't answer all part. So how do they relate to its position? So these are in group 1 and they're metals, and that's in group 16. You would look up the periodic table if you don't know, because that's why you're given it. And then explain how it forms. So when these atoms react with that molecule, and that's really about the exchange of electrons. So how do I go from atoms to ions? Now, because we will be running out of time, I'm going to just go straight to the assessment schedule, because you can see there's a lot of writing. So this takes you all the way to excellence level, but notice of those things we did, they gave you the electron configuration of the atoms, they gave you the electron configuration of the ions. And if you look at what they need, give the correct arrangement of either the two atoms or the two ions for an achieved point. Each of these counts for an achieved point, each of these bullet points. They asked you to relate it to where it is in the periodic table. So that's easy to look up. Oxygen is in group 16. Sodium and potassium are in group 1. They didn't give a point for that, which I thought was a bit mean, but anyway. But they did ask you in terms of why they react. And of course, if they're in group 1, they have one valence electron, so would prefer to lose that one valence electron. Now be careful of how you say things. Notice that the atoms lose the electrons, not the ions. So a very common mistake is to say K plus has lost an electron, or K plus loses an electron, something along those lines. Rather say K atom loses one electron to form K plus, because K plus won't lose any more electrons. It's not going to form K2 plus or K3 plus. So just be careful of that wording. And then refer to the valence electrons. And I did sort of show you right in the beginning when we were looking at the periodic table. Use these numbers. So group 1 has got one valence electron, group 2 has got 2. And then the ones on this side, you just simply go by the last number. So group 13 has got 3, group 14 has got 4, group 15 has got 5, group 16 has got 6, group 17 has got 7, group 18 has got 8. Okay, let's go. Oops, I've gone a bit too fast. And yep. And then basically, can you see how it talks about the transfer of electrons? If sodium and potassium atoms want to lose electrons, they'll be giving it to the oxygen atom because the oxygen atom wants to gain electrons. So if you've got all those points in there, then that'll you should get excellence. So the sodium and potassium atoms won't react with each other because you're not going to have the one gaining electrons. You're not going to get K minus or Na minus. So they're both losing and to form cations. And cations will also repel each other. So even if they somehow lost or something, if they both form cations, they're going to repel each other. Any questions on this? So the best thing when you answer, because this is a long answer, it's got lots of things in there. Notice how a layout makes it useful and clear because it's sort of step by step. The examiner can clearly see what you're doing. Remember in the exam, you can always get extra paper, but lay it out rather than just having a whole lot. Then once you've given your answer, then go back. Oops, I'm trying to get this. Go back and go, have I spoken about electron arrangements? Have I actually answered that first bit? Have I actually answered why potassium and sodium react with oxygen, but potassium won't react with sodium? You know, those two won't react. So make sure when you read your answer, have you done this? Have I done the electron arrangements of all three atoms and all three ions? Have I referred to its position in the periodic table? Have I said about that exchange of electrons to form that ionic bond? So you could even say, what is an ionic bond? An ionic bond is an attraction between two ions, okay, a cation and an anion. Right, so let's look now at this one. And here they've got this in terms of reactions, but now it's acids and bases. The moment you see litmus paper, you know this is about an acid-base reaction. So this, you know, is an acid. Hopefully you know this because we saw it in the first question. Hopefully you know this is a base or basic because it reacted with our other acid, our sulfuric acid. And now you've got to say what will happen here. Well, first of all, if you look at this, you know it's not an acid because there's no H in there. You know it's not a base because there's no oxygen or hydroxide or carbonate in there. So if it hasn't got one of those, you know it's not a base. So the only other option for this, it must be a salt. And at level 1, you only work with neutral salts. You don't work with acidic salts and basic salts. You learn that in level 2, in level 3. So basically what we're going to do with red litmus, remember, there are lots of mnemonics you can remember. Blue to red is acid, okay? Or there's lots of different ways you can remember this. So with red litmus, there's going to be no change, or you could say stays red, both of those. But if I put it into here, again, I'm going to get no change because it's neutral, so stays red. And this one is because it's basic, it will change and it turns blue. So give detail here. You could say red, red, blue, but it's not really a good look. Say it turns blue or it stays red. And now here, what will the reaction be with a carbonate? Well, an acid will be reacting with a carbonate to form bubbles or fizzing, anything along those lines. And again, use that first question to help you because you had a carbonate there with an acid. A salt is not going to react with a carbonate, so no change. And a carbonate is not going to react with a carbonate. Well, hydrogen carbonate is going to react with a carbonate, so there's going to be no change. Okay. And now you've got to write balance symbol equations, and they always put that S in there to sort of fool you in terms of there may be more than one equation, but hopefully you can see there's only one reaction. And they've actually done nearly the same equation as what we had before, except we've now got potassium carbonate and nitric acid. So it's a symbol equation. So if you like, you can first write the word equation, but you have got the formula for that. So use it, K2CO3. Yep, it's going fast. You've got HNO3, so use it. Everybody should be able to write that. And then because you've got fizzing, hopefully you know you've got CO2 and you've always got water. And again, your salt is going to be the cation of the base with the anion of the acid. So it's going to be KNO3. And look at the formula. Have I got it correct? On the table of ions, it's K plus, NO3 minus. So it's 1 to 1 ratio. So to balance, there's a 2 in front there. Okay, so that you need for an excellence level answer. And now what do they say? Explain the observations. So pretty much you will say this, again, I'm just going to go to the, just to save me writing it out. So you basically, okay, so there's no change or no reaction, something along those lines. Notice they've said stays red, turns blue. And really basically the carbonate is a base, so it's going to turn the litmus blue, and you don't need as much writing. All that writing was on your first part of this question. But it's pretty much sodium chloride is a neutral salt, so won't react. Carbonate won't react, but a acid will react with a carbonate to give a salt plus water plus carbon dioxide. And finally, whoops, in the 5 minutes left, we're going to zip through. Okay, here you need to do your ratio of ions. So basically you are back to the table of ions and work out that Ag plus, it's got 1 positive charge, and oxide in the table of ions has got 2 negative charges. So because this is neutral, now by neutral, I don't mean not acid or not base, I mean electrically neutral. It's not overall positive or overall negative. So you could say it's not, it's electrically neutral, or something along those lines, or if you just say it's just neutral. So that's why the silver has got a valency of 1, so loses 1 electron. Now, as I say, silver is one of those ones that you are but the odd one out, and lead is as well. But at least here you can just simply say I need 2 silver cations to balance the negative charge on 1 oxide ion. So that's fairly straightforward, as long as you explain it. So explain to a 2-year-old, do the obvious, okay? That the silver atom is going to lose 1 electron, and we know it's going to lose 1 electron because a table of ions said it's Ag plus. So if it's Ag plus, that means Ag atom must have lost 1 electron. And but the oxygen atom is too short of a full valence shell, and so it's going to want to gain 2 electrons to form O2 minus. So all those same things, just repeat again and again, all those obvious statements. And here's now, okay, so this is our 3rd equation where we give the balanced one. Notice how it always requires a balanced symbol equation for excellence level. And very, very quickly in the last minute or so, and really I just want to show over here, okay, there's a simple equation. When you have something like this, we say we're adding sodium hydroxide to our acid, and it's starting out red, or they don't even tell you what the color is, and you've got to say, and it says explain what happens when you're adding sodium hydroxide. Don't stop at the neutral point. Keep on going. Okay, so a lot of students will stop at green. Keep on going. So make sure you link the pH with the color, okay, and you keep on going. So here it turns green, but now you carry on going to blue and then to purple, okay. So keep on going, and yep. Then the other thing is link it, not just the pH to the color, but to the relative proportion of hydrogen ions and hydroxide ions. So if it's acidic, there'll be more hydrogen ions than hydroxide. I will stop in 30 seconds. If it's basic, you're going to have more hydroxide than hydrogen ions. And if it's neutral, you're going to have equal amounts of hydrogen and hydroxide. And there, okay, I've stopped. Yeah, so we're going to stop now, and I'll upload this to YouTube, and let me take the recording off anyway now.